Okay, so tic-tac-toe, the old-fashioned way, or we could do it our way, and our way is good because all right, okay, work optimal. Let's see, reveal, not the correct answer. I want submissions. Okay, too much work. I see. So you're saying the if-then way is too much work, so our way is less work. I think in the actual game of tic-tac-toe, our way, the RL way, the way I'm asking you to do it on the assignment is probably more work than the regular way. Like if you sat there, you could bang out a tic-tac-toe optimal strategy player with ifs and thens. It wouldn't be that bad. For tic-tac-toe, for that specific game, this way is actually easier. So this way is actually more work, the way I'm asking you to do it. So too much work is related. Okay. Yeah, it is possible. It would require specific every state and what to do. And that's too many states, so we're doing the RL way. Yeah, I think tic-tac-toe is right on the edge where in tic-tac-toe, there are not too many states. It's sort of like just big enough that it's okay. So this is the right sentiment. Sometimes things are too big and then the RL way maybe is better. But this is the right kind of idea. We're practicing because so that you can get good for the final project. So part of the reason I chose tic-tac-toe is you'll be training your tic-tac-toe thing with these RL things and value functions, and occasionally we'll do something crazy, and you'll be like, that is a stupid tic-tac-toe move. My function sucks. And then you'll know that it sucks, right? If I give you a really complicated game where you don't know if the move is good or bad, then you don't know if it's good or bad. So this is like your chance to practice in a simple situation where you kind of like have the alternate way in your mind. So as you go and you do these RL things, you can compare to the like really good strategy that you can like do on paper and see. So all these things like too much work or and so on, as the size of the game sort of grows, eventually this game tree method stops to be as good. So for example, in the game of chess, the game tree method is quite tough. You need to have a really good, what is called a valuation function to like look at a board and know if it's good or bad. And without that, it's quite hard. And so the bigger the game gets and the more it like branches out, the more like ifs and thens there are, the harder it gets. And tic-tac-toe is definitely doable. Pig-tac-toe is already big enough because the game is 4x4 instead of 3x3, and because the game goes until the end. In tic-tac-toe, the game often ends early, right? If somebody gets 3 in a row. Because the game ends immediately in tic-tac-toe, there's a lot of like forced moves. Those don't exist in pig-tac-toe. So that is the reason why we're doing it this way. There's one other thing I'm seeing anybody mentioned. Game tree is very large. Yeah, so all of these things, these are fantastic. These are the right answers to, like, in general, right? If you're trying to learn games, you want to do it this way with RL instead of the game tree, because the game trees get worse and worse and worse. They get sort of exponentially worse. But the RL methods, they can like effectively navigate the space in an efficient way and hopefully find some stuff. So these are great answers for the sort of general thing. I wonder, did anybody mention, because of this, intensive computations? Not in the course outline, yes. The reason the course is the way it is because the course is the way it is. Yeah, okay. The first rule of the tautology club is the first rule of the tautology club. Okay, yeah, okay. So there's one other thing that is different between tic-tac-toe and pig-tac-toe. So in tic-tac-toe, you could solve it with the if-then thing. But then if you took that algorithm and you tried to apply it to pig-tac-toe, there's one particular thing that would be quite thorny. Does anyone know what it would be? Yeah.
Well, there's chance.
That's right. That's right. So that if I, then you, then if I, then you, this sort of relies on knowing exactly what's going to happen. In pig-tac-toe, you say like, if I roll again, well, maybe I'll succeed, maybe not. So that makes the game tree much worse, because in a game like tic-tac-toe, you can sort of eliminate moves. You're like, I have to go here to block him from going here. That eliminates a whole chunk of the game tree. If it's a random thing, that can never be eliminated, right? So you cannot remove the possibility of me rolling a certain way, like it could happen a third of the time or whatever. So this kind of if-then thing does not work well, or it's like harder to get it to work on things that have randomness, whereas the RL ideas, they have like randomness like baked in everywhere. It's totally natural to work with randomness. So that's what we're doing. I don't know if you guys remember, in the very first day of class, I showed that video of the guy the Google guys who played Go. So they did the same thing, right? Go, in principle, you could play with and if I go here, then you go there. But they were using reinforcement learning ideas to get really good at Go, and they were the first people to ever beat the world champion at Go. And the reason is these RL ideas, they scale better to large games than the if-then things. Yeah, questions, comments? Okay, so that's why we're doing what we're doing. Let me say a couple more words about the assignment. So this is posted. I also just put up the grade scope. The grade scope this time around is very boring. Let me show you what the grade scope looks like. So here was my grade scope. For me, it'll show a couple games that are played. I don't think it'll print this out for you. For you, it'll only print out this. It takes whatever AI you give it, the my AI, and it plays against the two hard-coded AIs, the random move AI and the greedy AI. It plays 3,000 games against each of them, and then it calculates your score. So against the random AI, I won 1,259 times. I got 406 ties, and therefore my win rate is 48. In the win rate, a win counts as like a +1, a tie counts as a +0.5, and then it calculates your score out of 100, so 48 out of 100. It's not surprising that it's 48 out of 100. The AI that I tested here was the random AI. So it's like random AI versus random AI. It's going to be close to 50, and it's always, the 3,000 is enough games that you're within 1 or 2% of the true answer. The true answer should be 50, this was 48. The greedy AI, of course, is smarter than the random AI, and that's why my win rate was only 11. So when you try it on here, it's just to get like how good you are. Of course, you can run this yourself. On your computer, you have the two AIs, you can do it yourself. So why are we doing a grade scope? Well, one, so you can't like fake it, right? You can't say, oh yeah, my win rate was 99. Yeah, no problem. You gotta actually do it. And the other thing that's for fun that we're doing that's new is there's a new little tab over here called the leaderboard. And so I am now on the leaderboard with a score of 11 and 48, and anybody who submits, their scores will go on the leaderboard. It's just for fun to see how good you guys can get. I genuinely do not know what is the maximum percentage you can win against the greedy AI. So the greedy AI, some percent of the time, will play optimally. So I don't think you can beat it 100% of the time, right? Like, if it was playing optimally, it would tie you every time. But it's not playing optimally. How often can you beat it? Is it 70% of the time? Is it 80%? I don't know. You guys will find out on the leaderboard. The leaderboard is just for fun. So if you don't want people to know who you are, you can put in a fake name or a fun group name in the leaderboard, and we'll just have fun with it. Okay, that's the leaderboard. So that's what you'll do. Questions or comments about that? The other thing that I highly recommend, so I kind of threw this long code at you guys. I tried to add in lots and lots of comments so that it was readable. And this is like a skill I'm trying to like build with you, is like give you the code, you have to figure it out. So it's kind of like if you're like annoyed that you have to read this and figure out what to do, that's on purpose. I will say ChatGPT is extremely helpful for this kind of thing. So here is a little chat I had with it earlier where I attached the file. So it's helpful if you download it as a .py file. So it's all text, which is what ChatGPT is really good at reading. And I say, in the attached file, there's an implementation of tic-tac-toe. Can you explain how it works? And then it gave me like a nice summary of how things work. This was some of the stuff I went over last time. So everything's on a 3x3 grid. Here's what the numbers mean, right? If you have a grid, 1 means player X, 2 means player O, 0 means an empty space. And it has some stuff. Then there's it kind of goes through all the functions that are there. These are the same functions that are in your final project. So like create, k in a line, things like that, and so on. And then you can ask it things like, okay, so you can read all that, whatever. You can ask it really specific questions like, I don't understand how this part works. And I copied some function, the which 3 in a line. And this one has some weird stuff, like it has this funny jnp.logical.or. So you're like, what is this doing? And then it gave me a really nice explanation of how it works. So it's like, here is this function, here's an example, like here's winning in the top row, here's winning in the middle. Like it gives you all these examples and it really like spells it out for you, and it will be very patient. You can ask it as many dumb questions as you want, and it's great. So if you're trying to learn how it works, you can use this as a tool. I'm also happy to answer questions as well because I wrote it, so hopefully I know how it works. There's these inops. You might have never seen these before. These are doing operations on the rows and the columns. So for example, what is this which lines reduce? What is that doing? Well, ChatGPT explains it to you. This reduces the last 2 dimensions, R and C, using all, checking if every cell is in the winning pattern is true. The result is a Boolean array of shape 8, where true means the winning line is achieved. So it tells you exactly what it is. You can ask it more questions if it's not clear, And it gives a nice example. And then it gives a summary, and then it's like, hey, do you want any more questions? Here's some examples, things like that. So this will be helpful for you guys as well. It's a good place to sort of like, this is one thing ChatGPT is really good at. If you have like a specific code thing, you're like, how does this work? It's pretty good at that. Yeah.
Is this the paid version?
No, this is the free version.
Okay, cool.
Yes, this is true. I think it would eventually kick me out. It would be like, you've used too many free, you've used the like good model too many times, you're being downgraded. But even the free ones are really good at this. So yeah, highly recommend this. And the point, again, of assignment 4 is to help build you up towards the final project so that you have some of the skills you need. Okay, is there anything else I wanted to say? I don't think so. I'm going to throw you at it and do it. I gave you a little, on course link, I think in the announcement, there's like a little bit of here are the things you probably have to do. There are things like write the value function, add in some code that like remembers what happened in the game so you can use it to update later, things like that. So all the stuff we did in class as a little reminder for you, but you're going to have to fill it in yourself. Okay, questions, comments? Yeah.
What win rate do we need to get?
I'm not going to tell you that. Yes. So you got to make it as good as you can. You can see how other people are doing. I don't want to pre-specify because then it will sort of like reveal like how good you can possibly get, right? And this is like the truth in a real life situation. You're like, I'm working on my robot. How good can my robot be? I don't know. You tell me. So you gotta figure that out. I don't want to spoil it. Great question. Yeah.
Maybe it's in the description, but I can't remember. Does our AI always go first?
No, it's random. Yeah, you go first half the time.
Okay.
Yeah. Actually, okay, this is an important thing. So your AI will go first half the time and not go first half the time, but the board that is given to the AI to look at always takes the point of view of player 1. So you're always putting down a 1 in the square that you want to move into. Yeah.
In the code it's 1 for win, 0 for draw, and -1 for loss.
Yeah.
Does that work out the same as the 0, 0.5, and 1?
It's some linear function of whatever. You have to add 1 and divide by 2 or something. So yeah, I scaled it so it's out of 100. The reason it has to be out of 100 is the leaderboard will not accept negative numbers. So I could have put the raw thing in, but then the leaderboard would crash if you put in a negative number. So I scaled it to be between 0 and 100. Yeah, great point. Yeah.
So is that included in this summer? We're gonna have to do it ourselves.
No, it does that automatically. So you just submit the AI. You submit the function called my AI and anything else you need. Like if you have a function called value, you gotta submit a function called value, and then it should run automatically. I can show you the code that I ran in the leaderboard. Will be here under code. This is like what I submitted. So I said you have to import everything, and then you say definition my AI, and this is a copy paste of the random AI that has been relabeled. So it picks a random thing. Okay, great. So yeah, it is more open-ended than the previous ones. I also moved the due date back by 2 days. So the due date is next Wednesday, a week from tomorrow. And yeah, by then hopefully you should have something, and you try to make it as good as you can. And yeah, if you go all out and do a neural network, you can probably get pretty close to the optimal strategy, which exists and is pretty achievable in tic-tac-toe. Okay. Last minute questions or comments? Okay, we're gonna kick off today. So like, what are we doing in the rest of the course? Like, basically, you know all the stuff that you need in the course. Like, you know the main ideas. We have this idea of playing until the end, right? And then you use this Monte Carlo method to take the reward you get at the end and update your states. That is like the core idea. Everything else we're doing from now until the end of the course is just like upgrades. Like ways to make what we're doing before, still do the same thing, but do it better, do it smarter in some smarter way. And we're starting with a fun little example here of a soccer game. And we're gonna see how can we make the soccer game better. So here's the situation. Alice, Bob, and Carlos, they're a 3-person soccer team. Alice and Carlos are midfielders. Bob is a forward. And we imagine it's a Markov chain. So whoever has the ball, it's a Markov chain. It doesn't matter how they got the ball. They don't get tired or anything like that. Whoever has the ball, that will determine what happens in the future. And we're trying to understand what's going on. So, and we have observed 4 episodes. So it was like in the tic-tac-toe, you've played 4 tic-tac-toe games. You've played 4 soccer games. Here are the 4 soccer games we saw. In the first soccer game, Alice had the ball. Then we saw that Bob had the ball. Presumably Alice passed it to Bob. Then he scored 0 points. Then the game was over. In game 2, Carlos had the ball. Then Bob had the ball. scored 1 point, then the game was over. Carlos had the ball, then Bob had the ball, scored 0 points, then over. And game 4, Carlos had the ball, then Bob scored 1 point, and then it's over. So those are the 4 games we observed. And the first question is just asking you to do the Monte Carlo algorithm on pen and paper. So normally the Monte Carlo algorithm is in the computer, but for you, I want you to do it on paper. According to the Monte Carlo estimate, what is the value of each of the states? So these scoring 1 point or 0 points, those are the rewards. What is the value for each of the states? And then this is the exciting part. Once you have figured that, you got to fill in the blank on the following statement. I think the Monte Carlo algorithm blank the value of Alice having the ball, where blank is either underestimates or overestimates. So imagine the Monte Carlo algorithm says one thing. Imagine you're like a soccer recruiter and you're trying to figure out, is Alice good at soccer or not? Do you think the Monte Carlo algorithm is underestimating Alice or overestimating Alice? And then, think of why. Of course, in the multiple choice, you can't put why, but we'll talk about it after. Okay. Questions or comments about the question? Let me zoom out and give you guys a minute to think. Fill in the values for Alice, Bob, and Carlos, and what you think the algorithm is doing. Lexi, if you want to sit here, I can push this a little bit closer to you. There's a plug. Yeah.
So more so out of curiosity, my familiarity with the perfect tic-tac-toe strategy
Yeah.
that was lean and awkward in Wikipedia seems to rely a lot on the symmetry of the game. So how
Yeah.
would you code that in?
You can put that in your code if you want. One way you can do it is you can make sure that any parameters you have, like, symmetrically encoded. So for example, instead of having, like in the last class I did some features where I said, like, do you have something on the top line? So that's an asymmetrical feature because it's the top line. So you can have something instead that's like, you have something in the top line, or the bottom line, or the left, or the right. And then if the feature is like symmetric, then the function will be symmetric
So
too.
you could do something like get something on the
Yeah.
edge and something on the corner, something that's
Yes, that's right.
Ooh.
So this is like part of what you can be creative and figure out about it.
Okay, yeah, no, I was wondering, well, I think we're gonna put it easy just because I was curious just how that works, and it's
Yeah.
obviously it's an array, so I'm not sure how you would be like, okay, but if we're here, we should have 5.
Yeah, or another, I mean, if you want to do it that way, you can also tell NumPy to rotate it, things like that. So
Oh yeah,
Yeah,
I
for
know you
sure.
can like transpose it, right?
yeah, there's a rotate function. Yeah. Yeah. Okay. Okay, let's finish up what you think about Alice, Bob, and Carlos, and we'll go from there. There's 2 people who haven't entered yet. Okay, let's take a look. Alice, Bob, and Carlos. Who is the best at soccer? Let's see. Okay, reveal. Okay, so what does the Monte Carlo algorithm think when Alice has the ball? 11 people said 0. Alice, yes, this is the dehumanizing part of reinforcement learning. Alice has 0 value, unfortunately, for Alice. That is absolutely correct. How did the Monte Carlo algorithm calculate 0? Well, it said, take a look at every single episode where Alice had the ball, and we want to figure out what is the average of all the rewards. And there was only 1, and she got 0 points that time. So 0 out of 1, 0. Amazing. Very, very, very correct. What about when Bob has the ball? What does Bob have? 11 people said 1 out of 2. That is exactly right. Bob had the ball every single game. So we have 4 sort of samples with Bob. And so Bob has 1 point here and 1 point here. 2 points total and 4 simulations. So 2 out of 4, also known as a half. That is exactly correct. And what about Carlos? Carlos has 2/3. Very good. Carlos has 2/3 because there were 3 simulations where Carlos had the ball, and 2 out of 3 were scored in. So 2 out of 3. So you guys got that exactly right. The exciting thing is now I think the Monte Carlo algorithm blanks the value of Alice. I think 12 people think it underestimates. I also agree with you. I think it underestimates. So very nice, very, very good thinking. So here is the hard question. We have a mathematical algorithm, very nicely defined, and the mathematical algorithm says 0. If you run the algorithm, you get 0. And yet everybody in the class sort of agrees that Alice is being treated unfairly here, and it's sort of like the algorithm is underestimating Alice. Can we explain what is the reason, and why is it that the algorithm is like, quote, wrong, right? Like, what is the thing that the algorithm is doing that doesn't match our intuition as humans? Yeah.
We can get rid of samples.
Yes. Okay. This is a great point. So you could say the reason the algorithm is doing badly, is not very accurate, is because we only have 4 samples. And if we had more and more samples, the algorithm would get better and better. However, I think this issue about the number of samples is unrelated to the under, over, or correctly estimates. The number of samples sort of tells you how big the error is, but this is talking about the direction of the error. So it could be that we only have 4 samples and we're like, we're really unsure about the value of Alice. But in this situation, we're not only are we unsure, like we think there's a lot of error in the thing, but we kind of think that it should be higher. In stats class, you learn the term bias. This is exactly what bias is. So the number of samples sort of tells you the total error, but we're asking about the bias, and we're saying the bias is, I guess in this case, negative. The algorithm is below the average of what Alice should be. So given this information, we think Alice should have a higher score than 0. Of course, we're not going to be very accurate because we only had 4 samples, but we think it's higher than this. So I think it's the fact that there were only 4 episodes was so we could calculate exactly what's going on easily. As we get more and more, the error should go down, but I think it could always be, you could imagine a situation with like thousands of games where Alice is still underestimated. So yeah, that's a great point. I saw another hand over here, maybe?
I was just going to say maybe it's because we're initializing it. We're assuming that everybody has 0 value.
This is a good point. So I think if you remember, when we did the Monte Carlo, I guess I should have maybe been more explicit here. I wanted to do the Monte Carlo where we do the total sum divided by the number of episodes. It's true that later on we were talking about this constant alpha one. And if we did the constant alpha one, then it would matter what we initialize them at. But in the quote true Monte Carlo, no matter what you initialize them at, initially after the first step, it will be the average divided by 1. In this case, it's 0 over 1. So yeah, that's a good point as well. So in this situation, the initialization does not matter. That's a good point. Yeah.
Yeah, we were thinking it, but I figured I was overthinking when I thought maybe the Alice and Carlos would just be 0 since it's Bob that initiates the goal.
Yes. Okay, this is a good point. So remember, it's true that based on what we've seen, when Alice and Carlos have the ball, the rewards we get immediately are 0. So the immediate reward sort of Alice and Carlos is 0. Early in the course, we called this the reward vector, right? So the reward vector for Alice and Carlos is 0, but the value function is not just the reward vector. The value function is the long-term return. And so because they had the ball and then we eventually scored, that means their value function is not 0. Yeah, this is a good point. Don't mix up the instantaneous reward and the final reward. A good example is in tic-tac-toe, right? You don't win the game until the end of the game. That doesn't mean if you make a move, it could be a good move or a bad move, even though technically you're not going to lose till 5 turns later.
Okay.
Yeah.
I was just curious. I got all of it right. I just want to play devil's
Yeah. No, this is the whole point of this example, is so we can talk about it and discuss. So this is great. Yeah. Anyone else? Yeah.
Should you scale up the scores so that you're not getting reward of 0 instead of maybe point 5 instead of
Yes. Okay. This is a good point. So in from what we saw, we scored 0 or 1. You could imagine that the rewards could be negative, right? Like maybe Alice had the ball and then they got scored on. So in the examples we saw, it was always 0 or 1, and you might be suspicious of this. But I guess the way I wanted to interpret the problem was the rewards can be anything. You don't know what they're going to be, and we just want to go based on the samples we have, talk about what it's going to be. Yeah.
Is the value function underestimating Alice because we didn't really see Alice?
Yeah, right. Okay, so this is the same issue as before. We only saw one episode, and so like you're right. There's a lot of error. We don't know. Like we really have not a lot of information on how good or bad it is when Alice has the ball. But I would argue that not only is the information like uncertain, we have a lot of uncertainty around this value, but actually I think it should be higher than 0. And there's one comparison that I would make between two players over here. Does anyone has anyone thought of it this way, of comparing different players to each other to see how they are? Yeah.
So another way I'm thinking about it is that would they not earn points for making a successful like pass? So Alice made a successful pass rather than the other team getting the ball, and then so that would be like maybe 1 point, and then Bob only scored 2 of 4 possible shots that made like 50% or something.
Yes. Okay. This is exactly the kind of thing that I'm thinking of, which is that look. Alice had the ball. Alice did her job, which was to get the ball to Bob. And then Bob is the one that screwed up here at the end. So why is Alice getting a 0-pointer? It's all Bob's fault, right? You see, this is, and the way I think you can crystallize it, you can say like, look, Alice did exactly the same things as Carlos. But every time Carlos had the ball, Carlos passed it to Bob. Every time Alice had the ball, she passed it to Bob. Alice and Carlos, they both did exactly the same job. And yet the Monte Carlo algorithm thinks that Alice is a 0 and Carlos is a 2/3, right? And so this is like one way you can say that it's unfair, is that, look, the reason Alice is being underestimated here is because the one time we saw it, like sort of Bob happened to do a bad job. But we actually have more information on Bob. We know that Bob scores about half the time. So we sort of have this information about Bob, that Bob scores about half the time, which this is our middle line over here. We have a sample size of 4 for that. So we're the most confident we are about anything we are in this situation. That is the highest confidence we have. The lowest uncertainty is this line. And so it's kind of unfair that we're basing it on the one time that Bob did bad. We're basing Alice's total value on that one situation. We could get a better estimate by doing something different. Does that idea make sense to people? So let's think of what would be a better value other than 0. This is the Monte Carlo algorithm. Let's come up with, if we were making a different kind of algorithm, what value would we put for Alice? What value should we put? 1. Okay, let me write these on the board. Actually, I wanted to test out something in mathematics as well. So let's do this. Is option A. We're going to have options A, B, C, D, because there's a way in mathematics you can make a quick little multiple choice. So let's do a multiple choice. Option A will be 1. Anyone have any other suggestions of what the value of Alice should be? Yeah.
Do you expect the value of whatever Bob's value ends up being?
Oh, which is? What would you put that?
Half.
A half? Okay. Anyone have something other than 1 or a half? Yeah.
DNA.
Well, we want the algorithm to come up with something.
TBA, TBD.
Yes. So it's true that you will never know the true value of Alice using only 4 samples. But we want to make an estimate, and in the language of statistics, what would be a sort of unbiased estimate of Alice's thing? I guess, okay, let me add on 2/3, because that's Carlos's, and someone mentioned about Carlos and Bob, and I don't know, anyone have a different number that could apply to this situation? Let's put 1/4. I don't know. Okay. Probably 1/4 is wrong. Okay. let me run this as a quick vote, which is something I wanted to try. I'm going to add a quick vote. Add a quick vote. Okay. There you go. Hit me up with a quick vote, and I'll start that. And so you can pick A, or B, or C, or D. What do you think it would be the sort of unbiased or the fair way to evaluate Alice? Okay, let me give you 1 minute to try that.
There's no right answer, right? It's just both.
Well, I mean, I haven't said like what it means yet, right? So what we're doing math the backwards to how normally math is. Normally math, they're like people worked on this problem for hundreds of years. They sweated and died without knowing the solution to this problem, and we're going to tell you the answer to this problem in the first 10 minutes of class and not explain where it came from or who worked on it or why it's important. We're doing it in reverse. We're like, can we figure out what is wrong with this algorithm and how we can fix it? And then I will tell you the answer in a minute, which is the answer that people have come up with. Yeah, so it's true. Yeah, there is no right or wrong answer because I haven't said what we're talking about yet, or we haven't like phrased it in a precise enough way, but we will. Yeah, it's like morally, what is the fair thing to do to Alice? That's how you should feel, right? It's ethics class. Okay, very nice. Let's take a look at what you guys said. Labels. Okay, 8 people are in B, 4 people are in C. We got a couple people in A or D. I also like B. I think B makes the most sense. So, I can't reveal the correct answer. There isn't one, but I like B as well. Okay, very nice. So B was the most popular, and B is the thing. Can I get the original one back? Let's get the original one back. I go here and I hit this one. Okay. And the reason I think B makes the most sense is we want the value of Alice to be just whatever the value of Bob is. So instead of saying Alice got the ball once, and in that situation we scored 0 times, the way we're going to think about it is we're going to say Alice got the ball once. In the one time we saw her, she passed the ball to Bob. And so we can think of Alice gives the ball to Bob 100% of the time. That's what we know about Alice. That's the fair thing to know about Alice, is only to look at the part that sort of they were responsible for. And Bob, based on what we know about Bob, that we score half the time. So B is actually a subset of this idea that we should say that the value of Alice equals the value of Bob, and this is because that's what we saw 100% of the time. Uh, 100% of the time. Okay. So that is the idea. And the value of Bob, we saw Bob score half the time, and that's why their value is a half. Yeah?
I guess interesting another thing to consider. We're only considering the goals that they scored, but Alice and Carlos are mid/defense.
Uh-huh.
And Carlos has the ball most of the time. Does that mean that he defended the best?
Oh yeah, that's a good point. I guess we're thinking about this in the context of
So
our that's true.
Well, never mind.
We're putting it into our framework of you have a sequence of observations of states.
Mm-hmm.
This is a good point. Is that like if you see somebody who has the ball more often, then that might indicate they're a good or a bad player. But yeah, in terms of the value function, actually, that doesn't tell you what's going. Actually, you could be an extremely valuable player. You just like sit there on the sidelines and do nothing all game, and you just tap the ball in. Right when they're about to score anyway, you just tap. You're like, look at me. 100% of the time, I get the ball. We score. So yeah, actually, it's true. Value doesn't have anything to do with how helpful you are to the team. You could be a terrible team player and still have quite a high value. Or like the goalie probably has a really negative value. Every time the goalie gets the ball, we're losing. We're getting scored on. God damn it. But yeah, so it's true. Like value function is quite a bit different than like value in real life. But don't get mixed up. Okay, yeah, great question. Okay, and so this algorithm that assigns the same score for Alice and Bob, because we saw Alice give the ball to Bob, it has a name. It is called temporal difference learning. And in temporal difference learning, the idea is we don't wait until the end of the game. We try to learn just based on the time that has passed between one thing happening and the next thing happening. So we can learn something just from Alice passing to Bob without having to wait until the end of the game. And that's the next little topic we're going to do. I have a little video queued up here on temporal difference learning. Let's see if I can get it going. As usual, YouTube will probably play an ad for us when I hit play. Let me rewind and hit play.
If one has...
Okay. Gotta turn up the volume and make sure I think it's on normal speed. Okay, great.
To identify one idea as central and novel to reinforcement learning, it would undoubtedly be temporal difference learning. And that's coming from Richard Sutton and Andrew Bardo, some of the pioneers of modern reinforcement learning.
Actually, I'm going to pause the video here to say that earlier this week, Sutton and Bardo, the two authors of the book we've been following, they were awarded the Turing Prize, which is like the Nobel Prize in computer science, for their work on this stuff. So these guys were like into this reinforcement learning stuff in like the 90s, back before like computers could actually do anything useful, right? So they were like literally doing tic-tac-toe, and everyone's like, you idiots, like we can solve tic-tac-toe the other way. Why would you waste your time on this? But now they have the Nobel Prize. Okay, anyway, let's keep going.
So yes, I think this is worthy of a video. In fact, this is part 4 of my 6-part series on RL fundamentals. My approach will be to present...
Actually, you might recognize some of the stuff, right? So he is following the same book.
In fact, this is part 4 of...
The same book that we are, and we've done all these same things already, right? So we started with the Bellman equation. Dynamic programming was this idea from the first couple assignments. Monte Carlo was the thing we just did. And now we're moving into TD learning. Sarsa and Q learning are types of TD learning we're going to see. One thing that is interesting, the book does function approximation, like using parameters. They do it after TD learning. We did it a little bit before. You can do it already with Monte Carlo. I think the book kind of waits until the last minute to do this, where you can do it earlier. Okay, let's keep going.
My 6-part series on RL fundamentals. My approach will be to present temporal difference learning and the related algorithms of Q learning, Sarsa, and expected Sarsa as the result of making a series of adjustments starting from Monte Carlo methods, which we're already familiar with. The hope is to compress the subject so we can understand a lot in a short amount of time. And I do mean a lot. Among other things, we'll do a careful walkthrough of the mechanics, understand and compare performance, and get down to the fine-grained actions the algorithms take in different circumstances. If you're trying to understand RL, this will be a pretty efficient use of your time. So, in the spirit of that efficiency, let's get started. Now, normally I do a review of the earlier videos, but there's just too much. Parts 1 to 3 altogether is a little over an hour, which is the equivalent of, and I did the math, 73,000 Wikipedia articles. You just can't summarize that. So instead of a review, I'm going to just say, watch the previous videos. Or at least, watch the video right before this one. Otherwise, you'll be completely lost. So from this moment, I'll assume you've done that. Okay, now, as mentioned, my strategy is to propose temporal difference learning as an adjusted version of Monte Carlo. Specifically, the plain, on-policy, constant alpha MC algorithm we covered in the last video.
So this is exactly the kind of algorithm that I showed you guys last class, using Monte Carlo samples to learn about tic-tac-toe by doing those constant alpha adjustments. And TD is some kind of small switch, just like it was for Alice, Bob, and Carlos. So the main reason I want to show you this video is they have some nice animations and a nice little summary here. So
recall, which you better, almost all RL algorithms fall within the generalized policy iteration paradigm, where there are 2 components: policy evaluation, where we learn the value function of a fixed policy, and policy improvement, where we use the policy's value function to create a slightly improved policy. Now, the adjustment we'll make sits entirely within evaluation. That means we can study a Markov reward process, which is essentially a Markov decision process without action.
Okay, so what is he saying here? So remember, the point of reinforcement learning is to find good policies, right? We want to learn how to actually play tic-tac-toe. We want to learn what is the best move. But when we actually do stuff, the hard part is just evaluating what is the value function, right? If you know what the value function is, then you can do the step where you say, oh, if I know the value function, I'm going to pick the action that maximizes the value function. And so that is the improvement thing. Remember, there are all those gotchas with exploring and stuff, right? The epsilon greedy, all that. But none of that has changed. And so what he's saying is, if you want to learn temporal difference learning, all you got to do is learn how to do policy evaluation. So you got to learn how to figure out what is the value function. If you know how to do that, then you can also learn improvements by doing all the stuff we did before. Okay, let's let him keep going.
Also, we may reference state values instead of action values, knowing that these evaluation methods can be applied to both.
Right, so we're going to learn the value function v of s, but in real life, sometimes you learn q of s comma a instead, and you just try all the actions with epsilon greedy, and you treat that as the same thing, right? So we're learning v, but you could equally well be learning q, and it would be the same thing. Okay.
If that doesn't make sense to you, I think you know what to do. Okay, the adjustment addresses a disabling feature of Monte Carlo. That is, an episode must complete before values can be updated. And that's a problem. If episodes are long, learning can be really slow. That's because the transitions and rewards within an episode contain useful information, which MC delays learning from. If we could learn from those, that would change our policy within an episode, which would change, and likely improve, how we explore that episode. This changes the algorithm's behavior to something that's often more efficient than MC. So addressing this is important. But I should note, we'll see the adjustment has other effects beyond merely fixing this issue.
Okay, so what he's saying is, one of the Other disadvantages of Monte Carlo is you don't learn until the end of the episode. So in our Alice, Bob, and Carlos example, we said we're not going to learn anything about Alice until the end of the episode where somebody scores or doesn't, where we could have learned right away that Alice passes to Bob, Bob having the bullet we know is good, so we can learn from that. So by learning sort of right away, you can learn faster, and also you'll notice it is effectively increasing the sample size, right? From instead of having one episode where Alice got 0 points, now we can tag on that one episode where Alice passed it to Bob, and we can leverage what we know about Bob from 4 episodes. So we kind of boost the size of Bob. I think there was also, the reason I wanted to show you this video is there's a nice little animated explanation over here. But before we do this specific example, there is also in the textbook, there is one other very simple sort of Alice, Bob, Carlos type example that I will show you as well. Just to show you the idea. So we're in this chapter 6 called Temporal Difference Learning. And the example is called driving home. So in this driving home example, very similar to the Alice, Bob, and Carlos example, we are in a situation where we're trying to predict how long is it going to take us to get home. So if you're leaving the office Friday at 6 o'clock, you think it will take 30 minutes to get home. If you were doing Monte Carlo learning, you would not be able to learn anything about how long it takes, how to update your predictions until you got home. So when you got home and you realized it actually took you 43 minutes, then you would update. And actually this is in a nice little graph over here. So you're in the situation of leaving home, leaving the office. You think it's going to take 30 minutes, but it actually took 43 minutes. And so if you were doing Monte Carlo learning, you would say at the end of the day, when I got home, next time I leave the office, I should think that it takes a little bit longer than I thought before. So instead of taking 30 minutes, I should adjust my belief a little bit higher. And so that is on the left-hand side over here is the Monte Carlo. So Monte Carlo says it actually took 43 minutes. You thought it took 30 minutes. You should boost up what you think. You might notice by the time you got to your car, you thought it would took 37 minutes. That should also go up. All of these should go up towards the actual outcome. In contrast, the temporal difference learning we're about to see is updating not to the final outcome, but to the next estimate. So you can actually already know that leaving the office, it's going to take longer than 30 minutes, because by the time you got to your car, 5 minutes after that, you were like, hey, I actually think it's going to take a lot longer. That should help you figure it out. And another big difference is you'll notice in some of these situations, reaching the car, you think it should take longer in the Monte Carlo world, but in the temporal difference world, you think it should take less, because you see that by the time you exit the highway, things are going quite well. So the updates are done one step at a time, and the direction they are can be very different of this difference of do you wait till the end or do you update right away. So we're going to see an actual example in a second. This is sort of a dopey method, and the textbook has a nice little write-up of this example that they use. Okay. Okay, let's go back to the video. Any questions or comments before I hit play? All right, let's see what you guys think.
Now to visualize the adjustment to evaluation, I'll use a simple Markov reward process. We have 4 possible states, S1, 2, 3, and T, where S capital T is a terminal state. The possible rewards are the integers from -3 to 3, and there's no discounting. And just like in Monte Carlo, we don't get to know the distribution function. From here, we can visualize our sequence of states over time with this grid, and our rewards with this. Let me explain. I'll walk through an episode. For time t equals 0, we sample our first state, which happens to be S3. And then, with a distribution that depends on that state, we sample a pair of a reward and the next state. Then we do this again and again until the end of the episode. The reason I'm representing things this way is it makes sums of rewards clear. Each one of these horizontal lines indicates the reward accumulated so far in the episode. That makes it easy to picture the returns. For example, the return G3. It's just the difference between the levels at t is equal to 3 and the end of the episode. Next, let's remember our goal in evaluation. It's to estimate the value of each state, which we do with a table, we refer to that with a capital V. Now, what happens in constant alpha MC is we sample an episode to completion, then we'll apply this update rule for each time step of every episode. Let's see that for a few more episodes.
Okay, so I think one thing he didn't say is that the values are right over here. So based on that first episode, let's go back to it. So this is kind of an actual version with numbers and stuff of that thing we saw, right? We got these three states, S1, S2, S3, and we're like, what will be the total reward or the total return from these three states? Well, we have one sample. So for example, in this situation, we have the sample G7, which was pretty positive. And so we're going to boost up what we think of state 3. We're going to boost it up a little bit. That's the thing that's getting updated right now. And so after we go through all the states we saw, we boost them all up. We have some kind of estimate.
Episode.
Yeah, there we go.
Let's see that for.
Okay, and then at the end of all these updates, it turned out we think S1, we think that has value 0. Actually, we never saw an S1, so this is whatever we initialized it to. S2, we think is 0.557. I guess when we saw S2s, they didn't have a huge value. I guess we're probably mostly biased by this one, which had a pretty small update. We think S2 is pretty big, 1.78. We've done a lot of updates with S3. Okay, but let's see what happens when you keep going.
For a few more episodes. Now let's get into the temporal difference method. Let's say we just sampled this episode and we'd like to apply the update for the state at t equals 2. As mentioned, the issue with MC is that we need to observe until the end of the episode. So let's compromise that a bit. Let's say we just had to make do with only observing up until 4 steps after t is equal to 2, meaning we don't see the rewards beyond that point. The number of steps is an algorithmic input, so we call it more generally n. This means we need to update this in the update rule since it's only known at the end of the episode. We need to replace it with something. Well, we've observed some portion of the return, so we should certainly use that. The question is, what do we use in place of the unobserved part? Well, these things add up to G6, so we need something to approximate that. Wait a minute, that's exactly what our value function does. We can use the value of the last observed state as an approximation to G6. Here, the value is 0, but during the algorithm, it'll do the trick. And now we can see the TD method.
Okay, so I want to say this is exactly what we did with Alice, Bob, and Carlos, right? So instead of waiting until the end of the game to see what the score was, we said Alice passed it to Bob. We can just use what we know about Bob as our estimate for what will happen later on, right? So without waiting until the end of the game, we can just say Bob has the ball. When Bob has the ball, the value is about a half. So probably things will happen. Half the time we'll score, half the time we won't. That's why we can update Alice's right away, right after Alice passes to Bob. So it's the same thing over here. We're saying we want to update the state S2 based on over here. We can, instead of waiting all the way till the end, we're just going to wait 4 steps here. With Alice and Bob, we only did 1 step. But here we're waiting 4 steps, and we're saying we can do an update to move the state S2 closer to what we see based on here, and we can replace all the rest of the game by what we think the value of S3 is. So that's the idea in temporal difference learning. Don't wait until the end of the episode. Update sooner based on your current estimates. Temporal difference learning is also called a bootstrapping method. Bootstrapping methods are like when you estimate something from nothing, or like, so the joke is like you pull yourself up by your bootstraps, which obviously cannot work. But like we're trying to learn the value function v by using the value function v, which seems like crazy. Like how could you do that? Right? If you don't know the value function v over here, how can we know it over here? But because this one is later in time, we can actually get something from this. So because Bob is a forward, he has more samples where he scores, and we can learn about Alice by bootstrapping off of Bob. We can learn about the state S2 by bootstrapping off of the state S3. So let's see it in action. Any questions or comments before I hit play once again? Okay, let's watch it happen.
Here, the value is 0, but during the algorithm, it'll do the trick. And now we can see the TD method in action. though you'll have to forgive me, it's tricky to show the adjusted return like I did for MC a second ago on screen, so I'll leave that out. But outside of that, this is what it looks like to process a single episode. Notice how the value updates are applied within episode and are lagged by 4 steps. And obviously, this process repeats.
So once again, this dotted blue line is showing you what we're updating. And at this point in time, we're updating this state based on what we've seen over here. So you kind of like update based on the future, right? And the trick to updating based on the future is not that you have a crystal ball, is you just like wait a couple steps until the future happens, and then you update. That's why it's called temporal difference learning. You're learning by the difference in time between t equals 5 and t equals 10. That difference in time is what is letting us update the state at t equals 5 based on this temporal difference. That's where it gets its name. Yeah. Okay, and once again, in MC, you would wait till the end. Now we're just doing it as we go.
Very fortunately, just like in MC, we ultimately converge to the right answer. Okay, let's now review this more generally. It's called n-step temporal difference learning, and it's easiest to understand if we recall the Monte Carlo approach, where we used this update rule for evaluation. To be clear, this refers to the state at time t of the nth episode. Now in this...
Okay, actually I'm going to show you guys an episode in code, like an example in code. Let me leave this up while I do the code episode, and then I can show you what does this line look like in code. And this is exactly the kind of thing you're going to do in assignment 4, so it might be helpful for that. So, and the example that I have is the drunkard's walk. So you might remember the drunkard, right? He is moving left and right. We want to know the value function. What is the chance that the drunkard, I think I said gambler over here, but they're both the same. What is the chance they end up at the house rather than ending up falling off the cliff? And the reason I did this problem is because we know the true answer. So the true answer is known. It is x over n. So this is what I'm doing. The drunkard's walk. The true answer, remember, it was v of x equals x over n, where x is how far you are from the cliff. So the house is over here at position n, the cliff is over here at position 0, and the gambler starts at position x. And the value of state x is x over n. That is the chance that they end up at their house rather than ending up off the cliff. So we know the true answer, and that's very convenient for doing an example because then I can compare the algorithm to the true answer and see which algorithm is better. And the first algorithm that I implemented is the Monte Carlo method. So just using samples of the gambler's problem, how would it look like? Here is the little function, the Monte Carlo method. Here's the exact answer, x over n from before. And how does the Monte Carlo method work? Well, it has 2 parts, right? First, you make this history of what happened. So you write down every single thing that happened in the state history, all the rewards you got in the reward history. That's like sampling the full episode from the video, right? So waiting all the way until the end. And then this little loop, what it does is it loops over until the episode ends. So this is just like part 1, I think I called this part 1, simulating. Well, there's a part 2 later, so I guess this is part 1. Okay, so you simulate, you do this while loop, while not the episode is over, you update where you are. If you are done, if you reach the house or the cliff, then it's over. Otherwise, you just keep going. So you're always moving, and this is the line where things get updated. So this is like the Monte Carlo part where we update the state. The current state is apply the next state function to this. In tic-tac-toe, for example, this will be like playing the move in tic-tac-toe. In the gambler's walk, or the drunkard's walk, the drunkard moves by 1 step. So this is a big loop, and it loops over everything, and it just does the simulation the Monte Carlo way. And then at the end, after we're done simulating, right, so after we fall off the cliff or not, we set episode is over to true, and when episode over is true, then we finish, right, we go to the end, we break out of this while loop, and then we go down to here to part 2, which is to update what we saw. And to update what we saw, this is exactly the line that is, this line over here is what is written in the video, is we are updating the states we visited we update them by this alpha times g minus whatever we think it is. So we're pushing towards the value g. We push the value function towards g according to learning rate. Learning rate is also called alpha. So this equation over here is the same, supposed to be the same as this equation over here. Let's see if I can do a little these are the guys who won that's Bartow, and this is Sutton. Those are the guys who won the Turing Award. Okay, let's put these two things over here. Stop looking at me, it's weird. Okay, this guy, okay, all right. So I'm trying to show you that this line of code, value function of state plus equal learning rate times g minus value function of state, that's exactly this line over here. V becomes v plus alpha, that's learning rate, times g minus v, pushing the value function v towards alpha. So that is Monte Carlo, and you can see how Monte Carlo is doing. Here's a little plot of Monte Carlo. And the reason I can calculate the error is because I know the true answer, right? So in real life, of course, you don't know the true answer. If you knew the true answer, you wouldn't bother with Monte Carlo. But you can see how does the alpha value affect how quickly it converges and how noisy it gets, right? If the alpha is super, super big, it takes a long time to get there. If alpha is really small, then, sorry, other way around. If alpha is really small, it takes a long time to learn, but you're pretty accurate. If alpha is too big, then you learn quickly, but it's very noisy. Okay, let's see what temporal difference learning looks like instead.
Why
Yeah.
is that none of the errors converge to zero, or is it not
Yeah, well, at the end of the day, it's based on Monte Carlo samples. You need an infinite number of samples if you wanted to get it exactly down to zero. The theorem says that if you put them on the right alpha schedule and you took the episodes to infinity, then eventually it would converge. But for a finite number of samples, you will never get a zero error. Yeah, that's a good question. Okay, any other questions? Okay, let's see, what is the temporal difference learning?
Rule, we call this the target. It's what we move our estimate towards on each step. In n-step TD, we replace the target with this, which is the sum of discounted rewards between t and t plus n, plus our existing value estimate to approximate the remaining rewards, discounted by n steps. The reason we do this is because that's what's observable at time t plus n. Also, things are appropriately set to zero when t plus n is beyond the end of the episode. Now let's talk about n. As mentioned,
before we talk about n, so let me show you what this looks like. The simplest possible thing you can do is one step TD, only looking one step into the future. I'll show you TD with n steps, but TD with one step is easy to understand. Surprisingly, guess what you guys think TD with one step is called? It has a special name. It's called TD0. What? Well, it turns out there's another parameter called lambda. When lambda equals 0, it's like one step. That's why. But so TD0, temporal difference learning with zero memory, it just goes one step in the future. And let's compare this to what is happening. So remember, before it was split into two parts, right? First you do everything while that episode is over. You write everything down in your state history, and then only at the end do you learn in part two. So you do all the doing, then you do, when you're done doing all the doing, then you do all the learning. In temporal difference learning, you do both at the same time. So in temporal difference learning, here is what it looks like. So I have the episodes. There is no memory. There is no state history or action history. I just learn while I'm doing in the current loop. And so what I do is I get the new state. So maybe I can zoom in one step over here. So I get the new state, I get the reward now. In the gambler's problem, the reward now is always 0. In some other problem, maybe you get rewards as you go, but I get the new state and the reward now, and then I compute this thing called the delta value. The delta value is the difference between this estimate that you observe and what the value function is now. So delta value, it's the reward we get now, plus the value function of the new state, one step into the future, minus the value function now. So it's the difference between what we think the value is in the future minus what we think the value is in the past. And that is exactly what we are trying to estimate. It's this value, g minus v. It's not exactly g minus v, it's our estimate for g minus v. And then once we know that delta value, this is how we update. The value of the current state gets pushed towards by this delta value. And then we update the current state. And then, so we kind of learn, this is us doing and learning sort of in sync with each other in the same loop. They're not separated out. That is temporal difference learning, TD0. Questions or comments about that one? All right, let's see what the graph looks like. So just like before, I can show you how good the error is. And so just for comparison, I put Monte Carlo with alpha equals 0.01. I put it over there. And these are what the TDs look like. So again, it depends on the learning rate. If you make the learning rate too big or too small, here, if it's too big, then it takes you a while to learn. But look at how much faster it's learning than the Monte Carlo in all of these situations. So the TD can learn sort of right away because it learns as it goes. It doesn't wait till the end. So it can be a lot better. Okay, questions? All right, let's watch a little bit more of the video. He's going to talk about TDN, which is TD with n steps. I also implemented that one. It's very similar, except you got to wait n steps. You learn n steps into the future. So you got to have a little queue here. That's what this little last n states.pop does. It pulls the value from n rounds ago out. So you got to be a little more careful, but you can get this kind of graph where you can see like how does it depend on how many steps in the past you looked. Let's also listen to this guy talk about it.
It sets the lag between the time of the state whose value is being updated and the time of the most recent observation. And it's worth emphasizing, just like alpha, n must be specified up front before you run the algorithm. If you set this integer to 1, the algorithm is very eager to make updates. Values are updated after each individual reward. If n is infinite, then TD is identical to MC, since the delay is always greater than the episode length. Also, some terminology. Using a value estimate in the target is called bootstrapping. As we'll see, bootstrapping has major implications. So let's see that by comparing its performance to MC on a pure evaluation task. That is, the random walk example from the previous video. To refresh,
hey, he's doing the exact example I did. So instead of watching him, you can look at my code, but I guess he'll explain it as well. Maybe I'll just talk about mine for a bit, and if you guys want, you can go see the video after. So yeah, so just like alpha is a parameter that affects how you learn, this n value is also a parameter that affects how you learn. And if you set it really, really big, then you're just back to Monte Carlo. So if you're sort of waiting until the end, that's Monte Carlo. If you set n equals 1, that's the really nice one where you have no memory, so it's really easy to write down. And it can learn pretty well. So n equals 1 can learn pretty well. But if you do more steps, sometimes it can learn even better. And the reason is, you know, if we learn right away when Alice passes to Bob, maybe we're not like giving enough time for things to happen, right? Like maybe we'd be better off waiting up for a few passes to happen to see what Alice does. So you can kind of be a little bit too greedy with your updates. You know, with one, you can sometimes learn faster with more steps. So because the error is shrinking faster, we're learning more quickly. So that's the TDN algorithm. It is like a replacement for Monte Carlo, and it can learn faster by doing this learn right away technique. Okay. Any questions or comments about this stuff overall? Okay, I got one final question for you guys, and then we'll call it a day. Let's see if I can find my questions. Are they in with the this? Okay. And we got to go in the. You know what it was? It for sure was this guy looking at me. That's the tab that I need. Okay, here we go. All right. Here it is. Pros and cons of TD. So here are. So we've talked about how TD is can be more efficient in terms of episodes, right? The number of samples you need until it learns. The error is going down over time more in terms of episodes, but what about in terms of wall time? So which algorithm takes longer to run in terms of seconds on your watch? And then the other question is memory efficient. Which one is better for memory? And I think I gave you the option of one is better, the other one's better, or they're about the same. Okay, let's give you 2 minutes to think about this, and then we will reveal the answers and wrap it up. All right, there's like 20 seconds left to put in your guesses. Okay, let's take a look. Reveal labels. Okay, 9 people said Monte Carlo is better for speed. So even though temporal difference learning is learning faster per episode, 9 people think the Monte Carlo is better in terms of time. And memory efficient, what do people think for memory efficient? People are very split for memory efficient. Does someone want to tell me why they picked which one for memory efficient? Yeah.
I picked the Monte Carlo is better because TD is running more operations per single loop than MC is. So even if it's slightly less, like very marginally, it still technically worse.
Okay, yes. Let's look at the code. So this is the big difference to understand is exactly what you're talking about. Let me open this up. So the big difference is Monte Carlo kind of operates in 2 stages. So Monte Carlo has this first you run everything, and then only at the end do you do these updates. Whereas in TD, they're kind of like baked in together, right? In TD, you have the updates sort of effectively inside the loop. As you're going, as you're simulating, you're doing the updates. That is absolutely true. So how does it, I don't remember what you chose. What?
I chose that MC is better because...
Better for speed or for memory?
For memory.
For memory. Okay, so explain to me why that means that MC is better for memory.
Well, because then it doesn't have to store the value of the G's that it's calculating for every loop for the updates.
Yes. Okay, this is true. So I guess the thing is, so the G's are never calculated here. You cannot know the G in the Monte Carlo way. So in the Monte Carlo way, you need to find the G. In the temporal difference way, you don't find the G, right? You use an estimate for the G. And the only way to calculate the G is to keep track of everything that happened, and then at the end, you add them up. So if you look in this code, we have the state history, we have the reward history, and then I calculate the returns by adding up the rewards. So I do G, capital G is the sum of the reward history.
I was thinking more so like when you're doing TE,
Yeah.
also it doesn't really have to keep track of that sum for the
Uh-huh.
data of the final state. It also has to keep track of the sum for your states before then for the updates of some of the other states.
Yeah, okay, this is a good point. So in temporal difference learning, you never have to go, there's a fixed amount you go back in time, but you don't have to go back in time more than that. So for example, in the TD0 with no memory, you're always doing one step to the next step. So in the TD0, there were only ever 2 states on the go. There's new state and there's current state. So there's current state starts out as random. New state is like what happens from here. And then at the end, after we do our update, we say current state equals new state. So there's 2 states on the go. There's the current state and the new state. Whereas you're right, in MC, as we're going, we just have one thing called state that we're updating, right? But at the end, when we do all those updates, how do we do the updates? We needed, at the end here, in the part 2, we needed this whole reward history thing, and we needed this whole state history thing. So actually, when we were doing this part 2 update, for it to work, we had to write down in our memory every single state we visited and every single reward we got along the way. Whereas in the temporal difference learning, we sort of see the new state. So it's true, we have to write down one extra state called the new state, but then we use it right away, and then we forget what it is, right? We just like chuck it away. So in temporal difference learning, you kind of always have to know n, where n is the like length of time you're looking at. But in Monte Carlo, you have to learn the entire thing. So actually, temporal difference learning, in this controversial vote where it was very split, temporal difference learning is much more memory efficient. So temporal difference learning is better. That is the correct answer. Surprisingly, temporal difference learning is also faster as well. So temporal difference learning is better in both. It's better for memory, and basically the reason it's better for learning is also the same thing, is all this reading and writing to the memory is actually very slow. So the computer is pretty good at doing like updates, but if you want to read and write from memory many times, that's quite slow. So in this little update loop over here, this part 2 is kind of a slow part of the learning algorithm. So in this, the TD learning just kind of has one big loop and it's kind of doing its stuff and it's learning as it goes. in the Monte Carlo, this second loop, the part 2, is quite slow. And so I did a little comparison at the bottom over here, comparing how they were. It's not a ton faster. So this is Monte Carlo versus TD0. The Monte Carlo took 25 seconds, and the TD0 took 18.9 seconds. Both of them did how many? They did 50,000 episodes with the same problem. So it's a little bit faster, not a lot, but this is a big advantage to not have to store everything and then read and write to the memory a bunch of times in the TD. Yeah.
Is it always faster than MCU?
Well, I mean, it's like depends how you implement it, right? But like as a sort of general principle, the TD is faster. And again, it's because you don't have to write down as much stuff as you go. We're going to see later that memory is extremely valuable because you can use it in a different way to speed things up. So TD being more memory efficient means it will work better with other methods that also let you scale up. So you can use your memory to do something very smart. And if you're wasting it on the Monte Carlo, you have less memory left over to use on the smart thing that I will say in a few classes. Okay, let's stop there. See you guys on Thursday. If you have any questions or comments about the assignment, please let me know. It is a little bit more open-ended than the previous ones.